Assalamualaikum warahmatullahi wabarakatuh, and hi, welcome to MMJ 32603 Heat Transfer online class. Example 3-8 from our textbooks. Steam at ambient temperature 1 of 320 degrees C flows in a cast iron pipe with conductivity of 80 watt per meter Kelvin, whose inner and outer diameter are equal to 5 centimeter and 5.5 centimeters respectively. The pipe is covered with 3 centimeter thick glass wool insulation with thermal conductivity of 0.05 watt per meter Kelvin. Heat is lost to the surroundings at ambient temperature of 5 degrees C by natural convection and radiation, with a combined heat transfer coefficient of 18 watt per meter squared Kelvin. Taking the heat transfer coefficient inside the pipe to be H1 equal 60 watt per meter squared Kelvin, determine the rate of heat loss from the steam per unit length of the pipe, and also determine the temperature drop across the pipe shell and the insulation. A schematic diagram of the problem. We have a pipe which have a thick insulation. The pipe inner radius is R1, the outer radius is R2, and the outer radius of the insulation is R3. The temperature inside the surface of the pipe is T1, and the outer surface of the pipe is T2, and the outer surface of insulation is T3. Inside the pipe, the ambient temperature inside the pipe, or the temperature of the steam inside the pipe, is T infinity 1 with heat coefficient or heat transfer coefficient H sub 1, and surrounding the pipe or the insulation, the ambient temperature is T infinity 2 with heat transfer coefficient H sub 2. Okay, so first of all, we can draw a thermal resistant network for this case, which start with temperature of the ambient inside the pipe, and then we have resistance, which is convection resistance, to T1. T1 is the inner surface of the pipe, and another resistance which is inside the pipe, which is conduction resistance, to T2, the outer surface of the pipe. Another resistance, conduction resistance, inside the insulation, to T3, which is the outer surface of the insulation. And another resistance called convection resistance to the ambient temperature T infinity 2. So now we have the thermal resistant network for this particular case. Then the steady rate of heat loss from the steam that we want to calculate can be calculated using this equation. Q dot equal T infinity 1 minus T infinity 2 over R total, or total thermal resistance. Okay, so in the question we know T infinity 1 and T infinity 2, but we don't know R total. So we have to calculate R total easily. From this thermal resistant network, we know that the total of thermal resistance is equal to R1 plus Ri plus R1 plus R2 plus Ro. So this is the equation for R total. And we know that from the diagram, R1 is R sub I is convection inside the pipe. So R sub I equal R convection 1, which is happen inside the pipe. And we know from Newton laws of cooling, thermal resistance by convection is equal to 1 over HA. In this case, H1, 1 over H sub 1 multiplied by A sub 1. H sub 1 is given in the question, but we don't know A sub 1. But we can calculate A sub 1 because we know the radius of the pipe. So A sub 1 equal to pi R1 L. And we know we just plug in all the information that we got from the question. We get A sub 1 equals 0.157 meter squared. So we use this value to inside this equation. So we get R sub I, or thermal resistance inside the pipe, is equal to 0.106 degrees Celsius per watt. Then we want to calculate R1, R sub 1. R sub 1 is conduction inside the pipe shell. Okay, so it's conduction. So conduction for R conduction for cylinder can be calculated using this equation: ln R sub 2 over R sub 1 over 2 pi K1 L. And we have all this information from the question. We just substitute or plug in the values inside this equation. We will get R sub 1 or R pipe equals 0.0002 degrees C per watt. Next, we want to calculate R2. R2 is R inside the insulation, which also conduction. And we use the same equation, but now ln R3 over R2 over 2 pi K2L. So we get R2 equal 2.35 degrees Celsius per watt. And finally, we want to calculate RO, or R at the outer surface of the pipe or the insulation, by convection to the surrounding. So R convection 1 over HA. Now 1 over H2. H2 is given in the question, and A3 we have to calculate using similar step that we done for the pipe. Now for insulation, we will get A3 equals 0.361 meter squared, and we plug in all the values that we have and we calculated into this equation. We will get RO equals 0.154 degrees C per watt. Okay, now we can calculate the total resistance by adding all those values, and we will get R total equal 2.61 degrees C per watt. And now we can calculate the heat loss Q dot equal T infinity 1 minus T infinity 2 over R total. We know all the values for this parameter of variables. We just plug it in and we will get the heat loss is equal to 121 watt. This is heat loss per meter or per unit pipe. Okay, per meter pipe length. Okay, we can get the heat loss for the total of the pipe by multiplying this with the pipe length. Okay, all right, next we want to know the temperature drops across the pipe and the insulation. Okay, so temperature drop we can calculate using also similar equation with what we used before. Delta T for pipe, is equal to what? Is equal to across the pipe. Okay, the difference between T1 and T2. Okay, and we know the value of Q, and we have calculated R pipe. R pipe is R1. So we just plug in Q equal 121 and R pipe that we have calculated equals 0.0002 degree C per watt. We will get the temperature difference between T1 and T2 is equal to 0.02 degree C. Okay, we can use this similar approach if we want to calculate, for example, T1. If we want to know the value of T1, we can calculate using this similar approach because we know Q dot and we know R pipe and we know T infinity 1. So for example, we can calculate T infinity 1 minus T1 over equal Q dot Ri, and we want to know T1 equal Q dot Ri minus here, so minus T infinity 1 plus minus. So this is how we can use the similar equation to calculate temperature as well, not only temperature drops. Okay, next we want to know the temperature drops across the insulation. Similar approach here. We know Q dot and we have calculated R insulation. Plug in all the value and we get 284 degrees C. This is temperature drop. Okay, that is the temperature between the inner and outer surface of the pipe differ only 0.02 degrees C, whereas temperature between inner and outer surface of the insulation differ greatly different, 284 degrees C. Okay, note that the thermal resistance of the pipe is too small relative to the other resistance and can be neglected without causing any significant error. Okay, also note that the temperature drop across the pipe is practically zero. Temperature drop is practically zero, near to zero, and thus the pipe can be assumed to be isothermal. The resistance to heat flow in insulated pipe is primarily due to the insulation. Okay, due to this insulation. All right, we want to look into another example. Example 3-9 in our textbook as well. A 3 millimeters diameter and 5-meter long electric wire is tightly wrapped with a 2 millimeter thick plastic cover whose thermal conductivity is K equals 0.15 watt per meter Kelvin. Electrical measurements indicate that a current of 10 ampere passes through the wire and there is a voltage drop of 8 volts along the wire. If the insulated wire is exposed to a medium at 30 degrees C with a heat transfer coefficient of 12 watt per meter cube per meter squared Kelvin, determine the temperature at the interface of the wire and the plastic cover in steady operation. Also determine whether doubling the thickness of the plastic cover will increase or decrease this interface temperature. All right, this is the schematic diagram similar to what we have seen in example 3-8. And we can draw the thermoresistor network from T1, and we have okay, so this is T1 resistance in the plastic insulator and resistance in the ambient, right? So R plastic is conduction and R convection is for the convection outer of the plastic insulator. from T1 to T2 to T ambient, from T1 inner surface of the insulation to T2 outer surface of insulation to T ambient, the surrounding temperature. Then the interface temperature can be determined from, interface temperature is T1, interface between the wire and the insulator. Q dot equal T1 minus T infinity over R total. Alright, so we know T infinity, and we don't know Q dot, and we don't know R total. So we try to get those information by do some calculation. Okay, what we want to know is T1, right? And we have information of T infinity, but we don't have these two information, but we can calculate using all information that we have from the question. So Q dot is equal to the generated heat generated by the voltage difference inside the wire. Right, so Q dot equal the work or voltage difference inside the wire. We will get V multiplied by I. This is use Ohm law. We will get 80 watt. So Q dot is equal 80 watt. So now we want to know R total. R total, we have R by convection and R plastic. So we calculate R by convection. 1 over H is A2, A sub 2. We know H from equation, but we have to calculate A2. We know radius, so we can calculate A2. A2, plug in all the information or the values inside this equation. We will get A sub 2 equals 0.110 meter square. And we use this value inside this equation. We will get R convection is equal to 0.76 degrees C per watt. And we also have to calculate R plastic. R plastic is conduction. So conduction for cylinder, R conduction for cylinder can be calculated using this equation. We know R2 and we know R2, we know R1 and K. Plug in all those value from question, we will get R plastic equals 0.18 degrees C watt. So we add R plastic and R convection to get R total, which equal to 0.94 degrees C per watt. And we got all information that we have to solve. We need to solve this equation. Just plug in all the values and we will get T1 equal 105 degrees Celsius. So T1 is the surface or interface temperature. Next, we want to know, to answer the second part of the question, we need to know the critical radius of insulation of the plastic cover. So critical radius of insulation can be calculated using this equation. R critical equal K over H. K over H is given in the question. Plug in the values inside this equation. We get R critical is equal 12.5 millimeters, which is larger than the radius of the plastic cover. Therefore, increasing the thickness of the plastic cover will enhance heat transfer until the outer radius of the cover reach 12.5 millimeters. As a result, the rate of heat transfer will increase when the interface temperature is held constant, or T sub 1 will decrease when rate of heat transfer is held constant, which is the case here. Okay, so in this case, what is the function of another function of this plastic cover is not only to cover us from electric shock, but it's also to to enhance heat transfer so that the wire will be not overheating. Okay, so this insulation uh, uh, function is to enhance heat transfer, so it must be below the critical radius. Okay, if we want to insulate uh, the heat from going outside, then we have to have insulation radius that bigger than 12.5 millimeter or bigger than the critical radius of insulation. So that's it for this video. Thank you very much. See you next time. Assalamu alaikum warahmatullahi wabarakatuh.